Started from where we left. Okay, go ahead.
Maybe I'll pass this around and you can put your names.
Did you tell them that you are expecting the notes to be typed up?
So let me.
You told me, I'm trying to remind you.
So
I'm not trying to give you more job than I need to.
So I had done this over the email, but let me re-emphasize that yes, we would like the notes to be in a more formal way. You see, I mean, the reason is not to, of course the reason is to make you work, of course, because it helps you crystallize ideas, right? If you want to really put it down on paper, then you really have to understand what you're saying. Otherwise, it just comes and goes, and that's it, you're lost. So so you should write up. I mean, of course, right now you're writing them, and you can type them, and when you have questions, approach the lecturer, resolve the issues that you have while you're typing the lectures, and then go on with typing. So that's also part of the reason, because if you type up and if you think you haven't understood, you will approach the lecturer, ask him questions, him or her questions, and then go on. So, yeah.
Regarding sir's lecture when you write it.
No, sir's name is Varahan. Don't say call me sir.
Trying to understand and write it down. But
Okay.
when giving a PowerPoint presentation,
Okay.
if we have to focus on what the person or the speaker is saying,
Okay.
simultaneously if we have to jot it down the exact thing, it becomes very difficult. Since
Okay.
we are a bit relaxed, we already presentation is slides are available, we are a bit relaxed.
Okay. So okay.
What the speaker is saying.
Okay. So if it's a PDF lecture, you would prefer to have the slides in advance with you. No, or is that what you're saying? No. Okay.
After the lecture we can have. Yeah.
Yeah. Oh no. After the lectures. Oh, after the lecture, definitely. Yes.
Then
Yes.
we can, almost everyone is having their laptop.
Can I make an offer? I can give you a free copy of my book to everybody. Don't give it to anybody else. Yeah, that's my gift to you guys. I'll do that. I will download the copy to Amit, and Amit from Amit you can get a copy. How about that?
I will email them the copy. That means.
Exactly.
Okay. Yeah.
It's only 680 pages, but you get free.
But please don't print 50 copies in this printer. I mean, it will really run out of lot.
You don't have to deal with me. You have to deal with the Cambridge University Press. If the lawyer comes behind you, you have to answer them. That's all.
Okay. So
that will solve your problem. What I was thinking was the following. If you took the notes and then send me a copy, we can add examples. We can sort of create a primer.
yeah, so, well, okay, fine. So because not everything is on the slides, right? She's explaining things, and that's the. Okay. Okay. Yeah. Exactly. So okay. Fine. So. And that should go into the notes, is what I'm saying. Because, for example, he gave several homework problems yesterday, and those should be solved in the notes, not just homework problem for somebody to solve. But
You could become an author of a primer.
yeah, exactly. So,
I'm a proverb man. I told you I'm going to tell you one more proverb right now.
okay.
An inconvenience is an adventure rightly considered. An adventure is an inconvenience wrongly considered. So take it as an adventure in the right sense.
So he mentioned this yesterday, that the chances are if you are not understanding something, there will be a lot more people who will not. And I just heard these comments from some after Ellen's lecture that, oh, actually I didn't quite understand these parts, but I thought I'm the only one who didn't follow it. So you see, example.
One more. I was sitting around, a couple of people asked questions, and I have encouraged them to bring up those questions during the question session this evening so that everybody can benefit, and that's what we will do. Okay. Yeah. Okay. Let's start from where we left. We have a Z is equal to Hx. H is a m by n matrix. This is m by 1. This is m by 1. M are the set of all observations. X is the unknown parameter. We have already considered the case m greater than n. I'm now going to consider the case m less than n. This is the underdetermined case. This is the overdetermined case. And after doing this, then I will introduce you to the notion of 3D war and some other geometric interpretations of the least square solutions. So in here, what do I have? Z is equal to H. Okay, before that, maybe I will draw a little picture that will help us now. This is Z. This is H. This is X. This is M. This is N. This kind of a picture telling 1,000 words is really true. This is N. So what I'm going to do, first I would like you to think about it like this. Pick the first M columns. This is N minus M. Then you partition this vector X. The top portion is X1, bottom portion is X2. This portion is M. This portion is M minus M. You call this part H1. You call this part H2. In other words, you partition this matrix into H1 and H2, where there is a square block, is a rectangular block, M units of X, the rest of it X2. So I can now rewrite Z is equal to H1 X1 plus H2 X2. H2 X2. Therefore, you can write this as H1 X1 is equal to Z minus H2 X2. H1 is M by M matrix. I'm now going to assume my matrix H is such that rank of H is equal to M. You please remember the rank is minimum of M and N. M is less than N. So the rank is M. That means H is a full rank. If H is a full rank means what? There exists a set of M linearly independent columns of H. I am assuming the first, I have rearranged matter such that the first M columns are such columns. So I could isolate this M by M matrix. By virtue of this assumption, H1 is a non-singular matrix. Therefore, I could express H1 is equal to H1 inverse Z minus H2 X2. What is X2? X2 is a part of the solution I'm seeking. So the top part depends on Z, H1, H2, and also X2. So for every possible choice, what is X2? X2 is an arbitrary choice. For every possible choice of X2, there is a corresponding choice for X1. There are infinitely many possible choices for X2. There are infinitely many solutions. Therefore, in the underdetermined case, we have infinitely many solutions. So given this, how are we going to be able to pose the problem of finding a unique solution to the least square problem? So I need to be able to look at it from a slightly different angle. So the least square problem in this case is going to be decided like this. Among all possible solutions, I'm seeking a solution which has the least norm. One way to induce uniqueness. So you may immediately ask a question, why you choose that? Well, this is simply a starting point. If you didn't like this, if you like anything else, give me, I can accommodate that. So I'm just going to show this is not a final say, word of God, it is simply a starting point. I would like to be able to induce uniqueness. Yeah?
Does it matter how you order your columns?
I'm assuming already ordered the columns and rotated, permuted the columns and rows such that the first M columns of H are linearly independent, which is equal to the rank of M. That's right. I'm assuming I'm already done. If not, they will be distributed elsewhere, collate them, and also permute them, correspondingly permute that, so you can restore the relations. With me? Good. In other words, I want you to be able to recognize that in the overdetermined case, I don't have a solution in the sense of solution. What do you mean by solution? The left-hand side must be equal to the right-hand side. So in the case of overdetermined case, there is no solution at all. In this case, there are infinitely many. So either way you go, you have trouble. So in the overdetermined case, what is that we found out? We didn't find a solution, even though we call it a solution. So we don't call it a solution. What do we call? We call the least square solution. The least square solution is not a solution in the sense of solution, maybe the right-hand side is equal to left-hand side. The least square solution, what does it say? The norm of the difference between the left-hand side and the right-hand side is minimum. All of you? That's the idea. Good. And we will talk about some of those things geometrically very soon, but I would like to be able to get an expression for this estimation. So find an x such that alpha by 2 times norm of x square is a minimum when my x is not a free variable. My x has to satisfy this constraint. So that is the constraint. Z must be equal to h of x. So among all possible, given z and h, among all possible x's that satisfy this, I want the one that minimizes this. What is alpha? Alpha is called a penalty term, penalty constant. It can be 1. I simply want to give myself a little bit more freedom to be able to have a knob I can control. So you can think of alpha as a knob, a free parameter. It's called a penalty parameter. So in this particular case, what is that we did? Just to quickly recapitulate. I have j of x. I have z minus h of x transpose z minus h of x. And I minimized j of x with respect to x, where x belongs to the whole space. Is unconstrained minimization. You may wonder, why is that I didn't do this in here? There are infinitely many solutions. So z minus hx is 0, because I have a solution. So this term is always 0. That's why I couldn't use what I use here, there. So I had to look at the problem in a slightly different sense. But I always have to respect this. That's a constraint. That's the relation between the observation of the model. So instead of this, if you didn't like this, you need to be able to promote a thought process that could lead to in some sense, a unique solution, whatever be that. We can accommodate several different things. In the lack of any other thing, any other suggestion, this is a good starting point. This is only a starting point, this is not the end. Once you understand what to do in this case, you can vary this and do whatever you want and be able to satisfy whatever requirements you want to impose on the particular problem. All of you? So this is a constraint optimization problem. So the area necessary condition, sufficient condition for optimality is not going to hold good straight away. All of it may. You could not have come here without having done constraint optimization. What is the famous problem that we all do, irrespective whether you do BS in Timbuktu or Bangalore or America or London? The following problem. The perimeter is fixed. What is the shape that can maximize the area? All of it, my players? Come on, guys. That's right. It's a constraint problem. Do you all know why pipes are always circular? There's no square pipe. Why the cross sections of pipes are circular? For a given perimeter, the area of circle is the maximum, so that I can push things through. There's a problem in calculus of variation. So I have a constraint on the given circumference. I would like to be able to maximize the cross-sectional area. That's a very typical optimization, constraint optimization problem in univariate calculus. Every calculus book has a chapter on it. What is that we need to do? We need to do in a multivariate domain. So what are the standard techniques for solving constraint optimization problem? One class of method is called method of elimination. X. So in this particular case, what is that you can do? You can express x. So in this particular case, you can express x1 in terms of x2 and eliminate x1 and do an unconstrained minimization in x2 and then recover x1. So method of elimination is one possibility, but generally method of elimination generally works only for textbook problems, small problems, just to get a feel for it. Yeah. Much more elegant approach that is applicable to multivariate case is the method of Lagrangian multiplier. Everybody must have heard that, right? There is no univariate calculus book without having a chapter on Lagrangian multiplier. How many of you are with me? To how many of you Lagrangian multiplier is new? How many of us know? Do you see that? It's no yes, it's not no, it's always a maybe. So even though we talk about the binary system, true, false, the real world is a multivariate, is a multivariate logic, right? It's a fuzzy logic. I know, maybe not. That's right. But everybody knows it. So I'm now going to concoct what's called a Lagrangian function. So what is the idea here? A constraint optimization is recast as an unconstrained optimization problem in a larger dimensional space. You have to pay your dues. To solve constraint problem is always more challenging than unconstrained problem. Either you spend money in eliminating and convert it into an unconstrained problem, or you expand your state space by introducing the Lagrangian multiplier and do an unconstrained minimization in the X-needed space. If you are going to do this unconstrained minimization in X-needed space, you have to do dark mode equations. So you pay one way or the other, but the second method is much more elegant, mathematically beautiful. I can easily tap the resources from the unconstrained methodology, and that's what we are going to follow. So let us concoct a function called L. This L is going to play the role of J, the new objective function. L is a function of x, which is my x to be determined. I'm also going to introduce a new variable lambda. Lambda is a vector. What is going to be the size of the vector? We will see in a moment. X, is already know, is an Rn. So what is lambda? To determine what lambda is going to be, I'm going to now attach this plus z minus h of x. Okay, now L is a scalar valued function. Z minus h of x is a vector of size m. It is an error. It is an innovation vector that sits in the observation space. If I want to be able to convert this into a number, I got to do an inner product. So I do a lambda transpose. So lambda is a vector in Rn. Lambda is called the Lagrangian multiplier. I'm not going to go into too much into the theory of Lagrangian multipliers. There are books written simply on Lagrangian multiplier techniques. It's one of the thoroughly understood aspects of optimization theory. So what is the idea here? This problem, the solution to this problem is equivalent to minimizing this, x belonging to Rn, lambda belonging to Rn. How many are with me? So what is my L? My L is a function that maps Rn to R. It takes two inputs, vector inputs, and delivers a number. How do I calculate the value of that number? This number, my objective function to be minimized, and the number I create by converting my constraint into a number. So this is what's called equality constraint. In constraint optimization problem, there are two kinds of problems. One is a equality constraint problem. Another one is an inequality constraint problem. Inequality constraint problem is much more difficult and demanding. Lagrange solved this problem of equality. Lagrange is as old as mathematics, right? There is not much mathematics before Lagrange. Well, you may debate about this, but he is as old as mathematics. But the corresponding concept of deriving necessary and sufficient condition for inequality constraints remained open until 1940. Fritz John, Kuhn Tucker, they were the people who derived the corresponding necessary and sufficient conditions for inequality constraint problem. So optimization theory has a very rich and a cherished history, and much of what happened in inequality constraint happened about 50, 60 years ago. Compared to Newton, 60 years ago is yesterday, right? So I want you to understand, I want you to remember that this is an extremely active area of interest. Much of what we are talking about is generally done in optimization literature. In this particular case, I don't need tools from Kuhn-Tucker theory. I only need the basic results from Lagrange's contribution because our problem is a equality constraint minimization problem. Are you with me now? Where would a data assimilation person confront an inequality constraint problem? For example, you remember we talked about a dynamic problem where I want to be able to estimate the parameters. Many physical parameters may have the requirement of being positive. Thermodynamic parameters, for example, they have to be positive. When you estimate, it comes as negative, it is not what the paper is written in. So estimation techniques have to very naturally embed the requirement of parameters being positive. So I may have to say x must be positive. So that's an inequality constraint. Inequality constraints very naturally occurs in data assimilation. So what does it mean? If you want to be a successful data assimilation person, you must have a very good facility with all aspects of multivariate optimization, constraint, unconstrained. In the case of constraint, equality constraint, inequality constraint, and so on. For each of these cases, you need to understand what is the necessary condition, what is the sufficient condition. And then once you have these necessary and sufficient conditions, then you have to look at, it doesn't tell you how to find them. Are you with me? Okay, I will give an analogy. A bank has been robbed. What does the police do? They publish a picture of a suspect. Are you with me, please? They don't know who it is. But based on talking to several people, this is the sketch of the person. Then what do? Once they know the profile of the person they are seeking, then they, oh, does he look like him? No. Does he look like him? Does he look like him? Oh, he looks like him. Oh, I have to question him. Are you with me? So first characterizing the culprit, then going after and finding him. These two are two different problems. Same thing in here. Characterizing the optimas, characterizing the location where the optima occurs, necessary conditions, sufficient conditions. That doesn't tell you diddly about how to find them. Then you have to develop what's called algorithms for finding the minimum. And that's another whole chapter in itself. All of it, me? That's right. So I'm not going to go into the algorithms. I'm not going to go into the inequality constraint. I simply want to open up the thought process as to what are all involved in here. So let's go back and solve this problem. I have already talked about how to compute the constraints. How to compute the gradients of linear function, quadratic functions. So this is quadratic in x. This is linear in x. This is independent of lambda. This is linear in lambda. All of it, me? So what is that I now need to do? I need to compute the gradient of L with respect to x equated to 0, gradient of L with respect to lambda equated to 0. Why? This is an unconstrained minimization problem in the extended space. What is the basic principle of optimization? At the minimum, with respect to the independent variables, the gradient must vanish. So let's compute this very quickly. So what is this going to be? Alpha by 2, and what is that? Well, let's go back. What is that? You remember yesterday we did gradient with respect to x of this is equal to 2ax. Gradient of x with respect to A transpose x is equal to A. You remember that, please? And that's the formula we are going to apply. So this looks like A is identity. So gradient of this is, okay, I also want you to remember norm square of x is equal to x transpose x. So this looks like this with the A is equal identity. Therefore, this is equal to 2x. Familiar with me? That's right. So this is equal to 2 times x, 2 gets cancelled. Okay, now I'm going to be concerned with this. Now let's come back in here. Lambda transpose hx. This looks like A transpose x. Therefore, gradient of lambda transpose hx is equal to A transpose is equal to lambda transpose h. Therefore, A is equal to h transpose lambda. So this is equal to h transpose lambda. So this is going to be equal to minus h transpose lambda. All of it, me? I'm not simply writing the answer. I'm also telling you how to get them. Why? It is my experience, they could come up to this, and that's where the problem generally might arise. So I would like to smooth out rough spots. I hope I'm helping you. All of you? Good. Now, what is this going to be? So the contribution to the derivative from here is 0. How does this look like? That looks like lambda transpose A, that is equal to A transpose lambda, where in this case A is equal to Z minus Hx. So if I said A is equal to Z minus Hx, this term looks like lambda transpose A, that's also A transpose lambda. Therefore, of A transpose lambda is equal to A, but A is equal to Z minus H, that is equal to Z minus H. Therefore, this is going to be equal to Z minus Hx. I'm going over the arithmetic a little bit more carefully because I want you to get a good feel for this. So what is that I need to do? Okay, now if this is 0, this essentially gives rise to Z is equal to Hx. That shouldn't be surprising. That's simply the constraint. So the derivative of the Lagrangian with respect to the Lagrangian multiplier is a restatement of the constraint. So when I equate these two, what do I get? I get with a loss of generality, let me assume 1. Alpha is equal to 1. Let us just test that now. So this is X is equal to H transpose lambda. So I have to solve these two. And that can be solved very easily by X is equal to, X is equal to, so this is X, therefore this is equal to, Z is equal to H of X, X is equal to that, H transpose lambda. Yes? Well, just for the fun of it, otherwise you have to carry that burden through. I want to make life simple, I make your life a little harder. So without alpha is equal to 1 is a homework problem for you. Are you with me? Good. Yeah, come on guys. Otherwise I have to carry that alpha around. When I'm trying to introduce the fundamental principles, I don't want to clobber that with too many variables. But in the formulation I would like you to put that in. Okay, now what is H transpose? Look at the assumption here. My rank of H transpose, so earlier I got H transpose H in here H transpose. So H transpose, this is M by N, this is the N by M. So he is in principle is the M by M. My matrix H is of rank M, so this is non-singular. How many of you are with me? If this is non-singular, I have the right to take the inverse. Therefore, Lagrangian multiplier H transpose inverse Z. I can now plug this in here. So from here, I get my X is equal to H transpose Z. I would like to call it LS. So I have solved the problem. Now I'm going to collect the solution in here and discuss that. So what was the least square solution in here? XLS is equal to H transpose H inverse H transpose Z. In this case, XLS is equal to H transpose inverse Z. This is for the underdetermined case, this is the overdetermined case. This matrix is a matrix of size M by N. This matrix is a matrix of size M by M. Here the matrix is of rank N, here the matrix of rank M. How many of you have me now? That's right. So if you're a computer scientist or a scientific programmer wanting to develop programs for solving least square problems, you must have an input command to test whether M is greater than N. If M is greater than N, go this way. If M is less than N, go this way. In this particular problem, you do this. In this particular problem, you do this. All of you with me? Good. Now I'm going to summarize this and interpret it a little bit more geometrically. So far, these are all variational ideas. I would like to be able to provide a very simple geometric interpretation, and that comes from the so-called projection theorem. All of you with me? Come on, guys. Now, before I go further, I also want to demonstrate one more little thing in here, because that question has come up in private discussions again and again. So Z is equal to H LS. So I'm going to substitute this in here. If I did this, what am I going to get? H transpose, H inverse, H transpose Z. Okay, in this case, if I substituted that, Z is equal to H transpose, H transpose inverse Z. But these two get cancelled, so this is equal to Z. Are you with me? So what does this say? Here the error is 0. Here the error is always non-zero. And I would like to be able to interpret this case a little bit more geometrically. To do that, let us see what it is. So Z is equal to, what does H of X means? If H is I'm now going to pull in a geometric argument. So H of X is essentially Hi, Xi, I is equal to 1 to n. So H1, H2, Hn are the columns of H. X1, X2, X3 are the scalars, which are the components of the vector X, H of X. If you multiply, what happens? So H of X is essentially linear combinations of the columns of H. All of it, me? Okay. So I'm concerned with m greater than n, the overdetermined case. So let's look at this now. Let's assume this is the world of H, the world of what's called span of H. What's called a span of H? A span of a collection of vectors is nothing but the linear combinations of them. So if x, y are two vectors belonging to Rn, span of x, y is equal to Z, A times x plus B times y for all A, B belonging to R. Do you see what that means? So, for example, if I picked two vectors, x is equal to 1, 0. If I picked y is equal to 0, 1. These are two unit vectors. What is the span of 1, 0, 0, 1? The whole two-dimensional space. It's a set of all linear combinations. So, span of a vector is a linear space generated by the given set of vectors. Are you with me? This is 2. From here I'm coming to n vectors. So each vector here, Hi, is an Rm. So what do I have? I have a collection of n vectors, each of which is of dimension m. M is greater than n. How many of you are with me? That means I'm concerned with two vectors in 3 dimensions. M is 3, n is 2. How many of you are with me? Good. So the span of H is a subspace of the, this is a subspace of the n-dimensional space. How many of you are with me? That's right. Now, somebody gives me a vector Z. And where does Z sit? Z sits in Rn. Observation. This Z could either be part of the span or not be part of the span. If it is part of the span, I don't have much problem. So in measurements, generally it is outside that. So let Z be a general vector in here. Every vector determines a point, this is the origin. Now I'm going to quote a theorem that we all learned when we learned geometry for the first time, whenever that is, 8th standard. Whenever that is. What is the theorem? Given a point and given a line, what is the shortest distance from the point to the line? The length of the perpendicular. And that's the least square principle. And that's what I'm going to show. So Z is a point in the n-dimensional space. Instead of a line, so what is the geometric problem we all know? If the line is L, if the point is X, the shortest length from that is the length of the perpendicular. So the line, what is a line? A line is a one-dimensional subspace. instead of the one-dimensional subspace, I'm interested in the n-dimensional subspace of the m-dimensional space. Are you with me? All the algebraic vector space structures are there. I'm now going to be able to ask myself, so what is this? This is 90 degrees. So what is the analog of that? If I project this vector onto this, that must be 90 degrees. The projected one I should be able to get as h times x. In other words, I'm interested in finding the vector x such that h of x is the best representation of z when viewed through the eyes of this span of h. All of it, hey, that's the idea. Once we have this geometry, the derivation of this formula will come in two lines, and let's do that now. Everybody with me, please? This is an extension of this fundamental geometric property. Think about it for a moment now. Okay, so what do I want? I would like to be able to compute what's called the error. This is the error in the representation. So I'm trying to represent z looking through the eyes of the span. So this representation is an error. The error is equal to h of x minus z, or z minus h of x, that right? Z minus h of x. Z minus h of x. So what do I want? E is a vector. E must be perpendicular to the span of h. That's a geometric idea. Now I have to convert this into an analytic formula. How do I express? So any vector in the span must be perpendicular to that. So what does that mean? H transpose must be perpendicular to E minus H of x. So that means H transpose Z, I should say Z, sorry, Z minus H of x must be equal to 0. That means H transpose Z is equal to minus H transpose H of x must be equal to 0. Therefore, H transpose H x is equal to H transpose Z. And that's the formula that came from here. What is that? H transpose H of x is equal to H transpose Z. That's the governing formula. All of me? So I could have derived this from here. In other words, I would like to be able to enrich the beauty of the least square solution by looking at it essentially from a variational framework and then looking at it from a geometric framework. In either way, I'm going to be applying the same idea. All of you? That's right. How many of you are with me? That's right. It's one of the most beautiful. Okay, what is this? Those of you who are in math, yeah, go ahead. Is that? Okay.
H transpose is a matrix,
yeah.
And you wrote H transpose is perpendicular to Z minus Hx.
Every column of H must be perpendicular to E. So that's the condition. That's right. Now I'm going to introduce the notion of what's called a projection matrix. And that's going to further embellish this, and that's what my next job is. In other words, I'm trying to interpret the beauty of this. Why? I'm going to soon show that these are all going to occur as a part of 3D work. These are very elegant geometric point of view that we need to have a decent understanding as you go by. Good. So, are you with me on this? I can erase this part. So, Z is equal to H of x. X is equal to this. Therefore, Z is equal to H transpose, H inverse, H transpose Z LS. So this is the least square. So this is equal to Z LS is equal to that. How many of you know? So what is ZLS? This is the least square representation of Z. So Z minus ZLS is equal to Z minus H transpose H inverse H transpose Z. That's the error. Now I'm going to concoct some new matrices. Define, let PH equal to H transpose H inverse H. Before I go further, I would like to be able to introduce a couple of other notations too. Do all of us get that, please? What does that we know? If AX is equal to B, we call X is equal to A inverse B. Likewise, if HX is equal to Z, X is equal to H plus Z. Why I use plus instead of minus? In this case, when A is non-singular, the inverse exists. But H is a rectangular matrix. Matrix theory doesn't tell you how to find inverse. It's not even defined. But the generalized inverse of H is defined. The generalized inverse is denoted by this. In the case when H is a full rank, I have an explicit expression for the generalized inverse. The explicit expression for the generalized inverse is H transpose, H inverse, H transpose. Are you with me? That's right. So the notion of a generalized inverse. So the notion of generalized inverse for the over-determined case is this. The notion of a generalized inverse for the underdetermined case is H. So these are the two forms of generalized inverses, one for the over-determined case and the other for underdetermined case. All of it, me? Okay. The notion of a generalized inverse was defined in matrix theory in 1930s by Penrose, a British mathematician. It's called Penrose inverse, Moore-Penrose inverse. There are several different varieties, and there are books written on generalized inverses. One of the classic books on generalized inverses is the book by Professor C.R. Rao. He has written an absolutely delightful account of the computations and applications of Least theory, and it should not be surprising that C.R. Rao should have had a book on generalized inverse because he worked with Fisher. He worked on some of the basic foundations of estimation, and nobody writes on estimation like C.R. Rao does. And the book on generalized inverse by C.R. Rao is one of the most beautiful account, most elegant piece of mathematics. And what I'm trying to do is chapter 1 from that book. So the notion of generalized inverses is very fundamental and important. Okay, so generalized inverse I have introduced. Now I'm going to introduce another. Look at this. Look at this is slightly different. The generalized inverse is essentially H transpose, H inverse, H transpose. So that is interesting to express the estimate. Now I'm going to pull it all together. I would like to be able to get an expression for E. So in that process, does everyone understand the error is equal to Z minus the projected Z? This is the projected Z, this is actual Z. So I don't want to keep writing this. I'm going to concapt a symbol. This is a symbol, and what is this? This is called an orthogonal projection matrix onto the space spanned by the columns of H. Yes? 1 second. What the question, please?
You have a transpose of H.
Did I school? Yeah, you're right. Thank you. You're my compiler. A compiler is supposed to detect mistakes, right? Thank you. Thank you. Okay, there are two kinds of projection. One is called orthogonal projection, another is called oblique projection. How do I visualize orthogonal projection? You can think of it in physics, this is how they will explain this. Suppose this is the case, if you shine light in a direction perpendicular to the span, the shadow cast by Z on the span of H is the projection. If I show light in a direction that is not perpendicular to this, the shadow could be larger or shorter depending on the angle. So that's called oblique projection. So, what is the relation between orthogonal projection and oblique projection on least squares? Unweighted least squares gives rise to orthogonal projection. Weighted least squares gives rise to oblique projections. So before I go further, this is a projection matrix. So what are the characteristics? In matrix theory, they have already defined projection matrices. A matrix A is a projection matrix, is an orthogonal projection matrix. If there are two conditions, one, A is equal to A transpose, it is symmetric. I should say the first one. Then A is equal to A square, that's called idempotent. And two, A is equal to A transpose symmetric. Any symmetric idempotent matrix, by definition, in matrix theory, is called an orthogonal matrix. Matrix theory does this very beautifully. I'm not going to prove those. I'm going to now leave it to you to decide. If this is A, please make sure, exercise, homework problem, please. This times itself is equal to this itself. And this is also a symmetric matrix. So this matrix satisfies these two, therefore this is an orthogonal projection. Now what is an example of an oblique projection? A is an oblique projection if A square is equal to A. It's not necessarily symmetric. So if the matrix is idempotent, all idempotent matrices in principle represents oblique projection matrices. Symmetric idempotent matrices represents orthogonal projection. So in this case, homework problem, please verify this is an orthogonal projection. How many with me? These are simple things. You got to do it. Just have to do it. So in here, what is this? My E is equal to Z minus PHZ. This is P, that is that. So this is equal to I minus PHZ. So I can relabel them now. What is this? This vector from here to here is PHZ. And what is this vector? This is equal to E is equal to I minus PHZ. I minus PHZ is never 0 when Z does not lie on the space. If Z lies in this space, the projection is 0. Are you with me? Projection of a vector lying in a two-dimensional plane onto the two-dimensional plane is 0 because it lies there itself. Are you with me? That's right. So this is a beautiful way to be able to interpret the solution and also relate this to the squares. I'm now going to quickly talk about the oblique projection corresponding to the weighted least squares. Very quickly, I'm not going to belabor the point too much. Last class we had derived h of x transpose R inverse Z minus h of x. You remember that? This is the case when I have observational errors, and I also know the covariance properties of observational errors. We all know observation always have errors, but many a times we may not know what they are. If you have the luxury of knowing the observational error characteristics, you can formulate the problem by scaling as this way. If you don't, just forget and pray the Lord. Are you with me? Come on, guys. To be realistic, you need to be able to scale it. Okay. In this case, what is the least square solution? X least square is equal to H transpose R inverse H inverse H transpose R inverse Z. That's what you got. You need to check your notes. I'm now going to call this PH R times Z, where PHR is equal to H transpose R inverse H inverse H transpose R inverse. Are you with me? So in this case, so this becomes the orthogonal when R is identity. All of it me? So this is called the oblique projection matrix. Oblique projection matrix. I would like you to do that exercise. So the weighting changes the culture of orthogonal projection. Are you with me? That's the nature of the game. So we derive this formula as the old formula. So these formulas can be derived from two different ways. the geometric view as well as the variational view, and that's the first chapter. What is least squares? I've done only the linear least squares, overdetermined, underdetermined, and have explained. There are two topics I need to do: nonlinear least squares as well as 3D VAR. I'm going to hit the easy one first. I'm going to go to 3D VAR. I'll come back to nonlinear because it may take one full hour. I don't want to do some and then go over that. And we go till 12:30. We go till 12:30. Oh, good. Now I'm going to go to 3D VAR. How 3D VAR problems are natural extensions of these ideas. This is not a course in least square. This is a course in data assimilation. So I need to come back to variational methods for data assimilation. One of the standard methods is 3D VAR, and that's what I'm going to describe now. Before I go there, any questions?
Before you erase this.
Oh, I said, I can rewrite it.
No, next okay, doesn't matter. I guess the homework would like to suggest, but there was something missing in the formula. So fix it.
Which formula?
The one that you just erased.
Is that right? Okay.
So fix it.
Okay, good. Yeah, finding error is a puzzle, right? That's right, good. Yeah, that's homework too.
It's very straightforward.
Oh, this is oh, I said, okay. Thank you. Somebody's watching. I need to be more careful. Thank you. Okay, now let's motivate the 3D VAR. 3D VAR is a static version. Please. I want all of these.
If H is not full rank, in the case when n is greater than n, you interpreted that last time. For example, you are basically taking the measurements at the same time
That's right.
for all of them in the original problem, or it's effectively a problem with the model that you proposed. What's the corresponding thing for n is less than n when H is not full? Because you needed H to be full rank to find
That's
the
right.
least squares.
But
So what's the corresponding?
Very good question. In the case of underdetermined case, there's no projection needed.
But you
I'm
need,
lying in the same space.
no, but you needed H to be
Full rank.
full rank so that you can find H1,
That's
so that you can invert it.
That's correct.
Without that you can't do it. So
That's why the generalized inverse comes in. That's a very good question. I think it's good to tackle this at this point. Good, let's do that now. Z is equal to h of x, so I have assumed whether it is m greater than n, less than n, I have always assumed m is a full rank. What if I screwed my experimental setup? I didn't know my h is not full rank, and went ahead and did that. This formula always comes to help you. X least squares is equal to h plus z, the generalized inverse. So what do we need to do? We need to talk about how to compute generalized inverse of matrices when they are not of full ranks. I only consider the case when it is a full rank. When it is a full rank, h plus has an explicit form. H transpose, h inverse, transpose. When this is not a full rank, the algorithm, what do? They try to isolate the linearly independent columns and then use that in place of this h and compute that. That's why this expression is much more general than this. This is a very specific case that applies to generalized inverse when it is a full rank. When it is not a full rank, I don't have an explicit expression, but then what do you essentially do? You go and compute the rank, identify the linearly independent columns, and then consider that as a new h, and then do the computations. And that's part of the deal in computing the generalized inverses. So that is the reason I wanted to introduce this notation. This notation is an extension of this applies specifically when A is a full rank. This applies to any case and every case, but you can't give explicit expressions for that. There are very good numerical methods for solving this, and that's what I was referring to the book by Professor Rao. Are there any other questions, please? Good. Let's. So what is the motivation and where does this fit in? I have an unknown x I want to be able to estimate. I can collect information about it through observations, and let us pretend the observations and the unknown are linearly related. So this is one piece of information. Now we have seen if this is the only thing that you gave about the unknown, depending on whether m is greater than n, m is less than n, I can estimate x either as a overdetermined problem or underdetermined problem. So I have solved the first version of the data assimilation problem where I have only data to estimate. How many of you are with me? First chapter. What is the second chapter? That is a Bayesian connotation. In probability theory, when they introduced Bayesian analysis, what do they say? This is before the moon landing years, right? What is the probability there is life on the moon? Now we know. We didn't know before Armstrong landed on that. So we had always the probability. So when they introduce the Bayesian notation a priori, that relates to your belief, then you get evidences by way of observation. That's what's called likelihood. When the likelihood arrives, you need to be able to update your prior. The updated prior is called posterior. All of it, me? That's right. So in many situations, scientists know. A physicist may say, I don't know the value of the parameter, but I know for sure it is in between 0 and 1. It is greater than 0.5, less than 1.5. They know the range. That's the prior knowledge. A good scientist, even though he may not know the exact value, they have a pretty good idea of the range of values it ought to be taking. And that's what makes scientists unique. They have a feel for it. Okay, so they bring to the table what's called the prior. Such knowledges are called prior. In this particular case, a scientist may have a prior value, which I'm going to call it xb. xb. So he thinks xb is the value of x before any evidence came. So B for background. This background, in the case of meteorology, could be a climatology. For example, suppose somebody from the United States is planning a trip to Bangalore in December, and he is going to be around January 1st. He wants to see what that I need to pack. The climatology says the low temperature is about 10 degrees. The high temperature is probably 22, so I need a heavy coat, or I need a sweater, this and that. He arrives, he freezes over. Are you with me? Come on, guys, it can happen. So this is the climatological data before you arrive. After you arrive, then what is the combined estimate? So prior, the observation, and then I would like to get a new estimate, the posterior estimate. And that is the underlying concept of 3D war. Why this is called 3D war? Because x as a variable is a static variable. It's not a dynamic variable. All of you? That's right. So if I didn't have xb, I solved this problem by least squares. So it is not without reason we did least squares. Are you with me? So least squares is the fundamental foundations of deterministic data assimilation methods when there is no prior. You need to have a very strong understanding and foundation on that. Now bring in the prior. So what do I want? I want my x to be such that it is somehow mixes the information contained in here as well as there. Are you with me? Yeah. What is that? What is 1D war? So don't worry about 1D war, 3D war, let's not get into that debate. I call static deterministic estimation problem. Are you with me? That's right. The name 3D war is a misnomer. Why? If meteorologists calls it least square methods, the mathematicians will think, oh gosh, you are copying me, right? So every area, in order to solve their idea, they have to give a fancy name in their own world. So these are names concocted on the fly by meteorologists where they think they are able to capture. Now let me tell you one of the rationale for 3D war. The atmospheric variables are distributed in three-dimensional space. At a given point in time, I have a grid, I collate the grid, I have a vector x, they call it 3D war. That's why I told you, the roast smells the same by whatever name you call. So 1D war, 2D war, 3D war, I don't care. So let us call it static estimation problem. Are you with me? Okay, what is the probabilistic case? I assume the distribution of z. I assume the distribution of xb. Are you with me? Okay, so I'm not going to concoct a criterion function, which is j of x, which is going to be equal to z minus h of x transpose z minus h of x. You remember, here's our old friend. Old friends are always the best friends. What is the new guy? The new guy is going to be xb. Here comes lots of things. Did you give me xb alone? Or did you also give me the variance of my belief? So there are several shades of information that would come into play. xb, the covariance matrix of that. So what is B? B is the covariance of my belief that x is equal to xb before I took the observation. How many of you are with me? So if you didn't give me B, if you only gave me xb, how I'm going to concoct this? I'm going to concoct this as alpha by 2 xb transpose xb, which I would have said this is equal to xb squared. Do you remember what I did a minute ago? This is what I did. But if you give me the b, I would have said x minus x. Oh, I should have said, I'm sorry, I made a mistake. I should have said x minus xb transpose x minus xb. If you didn't give me the b, if you gave me the b, it will be x minus xb transpose b inverse x minus xb. In this case, z minus h of x transpose r inverse z minus h of x. So I would like you to think of two avatars of this. Are you with me? This is what I would use if you didn't give me any probabilistic covariance information. So this is the unweighted version. So what do I want? I want my x to be close to xb. I want my x to be close to h of x. So two people are pulling you. So what are you going to do? You are not going to leave either party. So you are going to pick a solution. So what is the basic idea? You are going to pick a solution that is going to be a linear combination of z and xb. So this is the unweighted version. This is the weighted version. The weighted version takes care of the weights which are inverse to the covariance matrices. Okay, now I would like you to relate to the probabilistic structure. Suppose Z is probabilistic, and I know, yeah. Louder. I want all of.
Suppose for one we have the error covariance matrix,
Uh-huh.
and for the observation space we don't have. So for that case we ignore the.
Well, you can do many things there. Are you with me? That's right. I'm not going to say which way would be the best way, because you can debate about these things. If you whatever you did, you should do to the same thing to all the terms. That's my preference.
Suppose if we are not having one, so we ignore that.
I would then do two things. Ignoring this I will do, with this I will do, and then I have to interpret. Hey, there's no easy answer being a scientist. A scientist has to take responsibility. And when in doubt, you do it every possible way. Are you with me? That's the best way to do. Did all of you hear the question, please? If I knew one but not the other, you have to do whichever way is possible. And then interpret it. And then say, and then argue, because of this looks better, because of that looks better, and so on and so forth. With me? So I'm not going to give you a solution to a question. I'm going to give you pathways of arguing about the solution. I'm not a judge. You should never play a judge or a jury. You should take you should go wherever it takes. That's science, right? That's right. All of it, me? Okay. Now I also want to tell you one more. if I have a function f, if I want to find the minimum of f of x, the location where the minimum occurs, if I have a function alpha times f of x, if I have a function alpha times f of x plus b, minimize this, minimize this. If I multiply a function by f means what? I'm scaling up or down. I'm not changing the locations where the maximum occurs. I may change the value of the maximum, but not the locations. Adding a constant, I'm pulling the function up or down uniformly. I'm not changing the locations where the maximum occurs or not. So because of that, I can multiply this function by suitable constant. This is the quadratic function. When you compute the gradient of a quadratic function, there's an annoying factor 2 keeps coming. To knock out that 2, generally you have a half. I didn't introduce this half until now. I have been carrying that, but I want you to recognize these are facts that comes from basic properties of functions. I can. Where is coming from? Okay. Alpha positive. If what happens, alpha is negative. That's right. You are going to fit the function. So if I don't want to change the locations, but so the maximum will become minimum, minimum will become maximum. Alpha, I'm assuming positive. Beta can be, B can be positive or negative. In which case you push it up or pull it down. That's right. With me? How many are with me? I want to emphasize the, okay. Now I would like to bring in the probabilistic notions that I was talking about yesterday as well as this morning. Suppose Z is Gaussian. Z is conditionally Gaussian. What is with me? The variance that. So what is that? There is 1 over square 2 pi to the power m by 2, because Z lies in m-dimensional space. The covariance are to the determinant, the square root of the determinant of that, exponential minus 1/2 Z minus h of x transpose or inverse Z minus h of x. That is the expression for the full-blown multivariate Gaussian distribution when Z is conditionally Gaussian given x. How many of you know? How many of you know the expression for multivariate Gaussian distribution? How many of you know the functional form of univariate Gaussian distribution? Let me say B of Z, 1 over square root of 2 pi sigma exponential minus 1/2 of Z minus m squared divided by sigma square. So this is for a univariate Gaussian. This is for a multivariate Gaussian. How many of you are with me? R is a known constant. You need to know these things to be able to see the bridge. You remember the very first talk Chris talked about? There is a parallelism between the variational as well as probabilistic. That's what I'm trying to tell you here. Now look, let's look at this part. What is this? That's the exponent. You remember? So I would like to be able to say this j of x is equal to j naught of x plus jb of x. What is j naught of x? Is the part of j comes from the observation, the part of the j that comes from the background, which is the prior information. So given this notation, can I write this as 2 pi to the power m by 2, determinant that exponential minus j naught of x. Everybody should remember there was a slide in Chris's talk with this. All of it make sense? So I took the log of this. So this is called likelihood. So there is an estimation technique in statistics which is called likelihood estimation technique. So there are several estimation techniques that are widely used: least square estimation, likelihood estimation, moment-based estimation, method of generalized moments. So there are several techniques for estimation. Data assimilation relates to estimation. So which of the methods are we going to use? We have concentrated on using the least square method. But I'm also going to relate the power of these squares to the likelihood. Least square and likelihood estimates are essentially the same when the underlying distributions are Gaussian. So the maximum likelihood estimate is essentially the least square estimate when the distribution are all Gaussian. That's a beautiful bridge. Do you see that, please? That's the relation between the two approaches. So I just want to provide the point of contacts. I'm not going to go into the probabilistic mode right now. Maybe we will revisit when we do the Kalman filters in a couple of days.
Can I make a
Please, Boris.
Yeah, but if you then take the exponential of the whole expression, then you can
The
separate
product of the expectation. So that's right. So I simply wanted to have that aha because I just did that. But exponential of this, we all know what. So what's being talked about? And then I take the log. That is me. So there are a lot of beautiful theory, and in our book there are 4 chapters wherein we describe the fundamentals of statistical estimation. That is me. It is, if you are going to make a living out of data assimilation, you have to learn it, and learn it when you are young. And you are all very young compared to many of us. Are you with me? Come on, guys. It's an investment in life you are going to make. Please don't postpone. Please don't postpone. Why? The earlier you put the money in the bank, by the time you retire, it grows, right? Knowledge is same. So you catch the knowledge early, put it in the bank. Okay, so is the formulation clear? 3D war, 1D war, 2D war, whatever war you are going to talk about. So where does 1D war, 2D war, 3D war differ? The way in which X is defined. If X is defined over a one-dimensional grid, my friend is right. If it is three-dimensional grid, so depending on the problem. Okay, now what is the best estimate? The best estimate for X is the one that minimizes this J. Do you see a lot of exercise coming in now? Come on, guys. That's a quadratic function. That's a quadratic function. The gradient of this we have already seen. But this guy is no different from here, essentially a quadratic function. Everybody? That's right. So I have to compute. So if you look up in meteorology papers, they will always say like this. The background term, this term, so the gradient of J is equal to gradient of J naught plus gradient of JB, gradient of JB, and set it to 0, set it to 0, set it to 0. I'm going to write down, because this is the first time we are doing this, so let me quickly write this down. So 1/2 Z transpose minus Z minus 2 times Z transpose HX plus X transpose H transpose HX. Please check that. X transpose X minus 2 times X transpose XB plus XB transpose XB. Now, I also want you to remember, is it X minus XB or XB minus X? It's a quadratic form. It really doesn't matter, right? That's a square term. So what is the gradient of this? Gradient of J is equal to, this goes to, the gradient of that is 1/2 0 minus 2 times H transpose Z plus 2 times H transpose H. That comes from here. 2 times H transpose, I'm sorry, X, that comes from there. I'm not going to belabor the issue, right? This is a linear term, this is a quadratic term, we all know, we have done it twice. I'm not talking like a broken record. Are you with me? I have introduced all the basic tools. You simply keep applying them again and again and again in different notations, in different circumstances. Hey, that's it, guys. No more. All of it, me? That's right. Plus 1/2 of Okay, what is this? This is 2x minus 2 times xb plus 0. So let us collate all the variables. So I will kick all the negative terms to the right-hand side. That H transpose Z plus XB comes in here. The other term is H transpose H plus I times XB. So what is the equation? My equation is H transpose H plus I times X is equal to H transpose Z plus XB. Therefore, my X, optimal X, which is called X star, is equal to H transpose H plus I inverse H transpose Z plus XB. How many of you heard me? So if there is no XB, there is no I, that is 0, I get back the old solution. So now you can see the right-hand side. This is the prior belief. This is the new observation. My X is going to be a solution of that. My X is going to be a solution of that. X star is the optimal solution. Well, this is X. That's right. Thank you. Thank you. Thank you. You're right. How many heard me? Good. Now, what is the homework for you? The homework is insert R inverse, insert B inverse. Come on, guys. You got to do this. Now you know that's why I didn't do it. So what is that? What will be the change? The change will be there will be an R inverse in here. The B inverse will come in here. There will be an R inverse in here. There will be a B inverse XB will come in here. I have already given you a solution. You simply need to check. All of me? That's right. So this, what does it tell you? When there are two pieces of information, you can't ignore either. You have to be able to take into account. You have to be able to take into account. So this solution essentially takes care of that. This is the underlying principle of 3D wire. So in meteorological circumstances, what is this? I have a region which I can think of it as a rectangular parallel pipette. You are considering 100 kilometer, 200 kilometers, 10 kilometers embedded grid. I'm interested in temperature. I'm interested in pressure. I'm interested in U velocity. I'm interested in V velocity. So at each grid point, you may have 6, 7 physical variables. The 3 velocities: temperature, pressure, humidity, water vapor in all forms. All of it, me? That's right. That's right. And if you go high, that could be ice crystals. So at each point, you have to worry about. So what is that X? X is a concatenated vector. So what is the size of X? The size of X is nx, ny, nz. So n is equal to nx times ny times nz times L. What is L? L is the number of physical variables. You are interested in 6 physical variables at each point. So that grows in a hurry. Now I would like to talk about next few minutes. So what does this relate to? Before lunch break, I would like to talk about this now. All these problems, whether it is a overdetermined problem, an underdetermined problem, or a 3D wire problem, look at that. What is an ultimate mathematical problem? I'm interested in solving a linear system where the system matrix is symmetric and partially definite. Yeah. Loud.
Doing this exercise by tomorrow morning would be really useful, or I would say really essential, because Eric's lecture tomorrow will be on ensemble Kalman filter, where he will, so to say, refer to this formula.
This is coming again. And
This will keep coming back again and again and again.
That's right.
So and in particular tomorrow morning lecture. So I think it will, if you derive it soon, then that will be very useful that you know what he is talking about tomorrow morning. And
one more point of contact. How many of you know Kalman filtering? We will revisit this in Kalman filtering too. In Kalman filtering, what will happen? There is a prediction which is the background XF. There is a new information Z. I want to combine this. So at the computing analysis, do you remember the notion of analysis was introduced by Chris in the first class? So if I have a forecast, the forecast plays the role of my XB, Z observation. So what happens in the, you remember the formula that he gave? XA is equal to XF plus K times. He used Y, I use Z. That's it. Hey, this is the formula he gave. What is that? This is the Kalman gain. This computation is no different from this computation. So what Kalman filter does is essentially a 3D VAR at each stage. So you start with the initial condition, you predict, the prediction becomes the background, you get the observation, 3D VAR, analysis becomes the new initial condition, go forward, keep repeating. So 3D VAR is absolutely fundamental to many things we do. And what is the underpinning theory behind 3D VAR? Least squares. That's why we spent a couple of hours in talking about least squares. That's where everything begins. Yes?
Is the background following these static in 3D?
In the case of Kalman filter, you have to dynamically pull that. You have to predict both the state as well as that, and that's where the rubber meets the road, and that's where the challenge comes in. We'll talk about some of those things. But are there any other questions, please? I would like to make one or two computational comments before we break for the lunch. I won't keep you for too long. Good. So what is that we want to do? We want to be able to solve Ax is equal to B, where A is SPD. What are the standard methods for solving this? One of the standard methods for solving this was called Cholesky factorization. So in number theory, what is the basic result? Given any number can be uniquely expressed as the product of powers of prime. That's a multiplicative decomposition. In number theory, there's also another decomposition called additive decomposition that leads to what's called partitions. A number can be expressed as sum of partitions. That's what Ramanujan excelled. You all know that. His fundamental results are in trying to compute the number of partitions for a given integer. But much more earlier result is given a number can be expressed uniquely as a product of powers of prime. So multiplicative decomposition, additive decomposition of numbers has been around for a long time. In matrix theory, there is a corresponding result. Multiplicative decomposition, additive decomposition. So multiplicative decompositions are A is equal to LU. A is equal to G transpose. This is for any general matrix. If A is SPD, I can express this G transpose. This is called Cholesky. So Cholesky decomposition can be applied, and what is the, so if this is an n by n system, what is the computational cost? Is the order of n cubed. I would like to take 2 minutes to be able to tell why this is very difficult. We all talk about logic problem. Somebody in here talked about logic problem. I think people have changed their seats. I had a picture of seat and the faces, but my picture has changed. I have to change my image now. Well, hey, don't sit in the same seat. Change the places. I'll find someone who used to ask that question, large problem. Is he here? Oh, you're the one. That's right. So I'm going to show what is the power of large. So let us suppose my n is 1,000,000, just for the fun of it. So an algorithm is going to take n cubed. So if algorithm takes n cubed, n is 1,000,000, what is the total number of operations my algorithm has to perform? Is the order of 10 to the power of 6 cube, which is 10 to the power of 18. That's a flop. Must be done. What is the best machine money can buy today? The best machine money can buy today can perform one flop in 10 to the power of minus 9 seconds for a flop. What is a flop? Flop is a floating point operation. It's the addition, multiplication, subtraction, division. So if this is the best I can do, if this is the number of work to be done, what is the time required to solve a problem of size when n is a million? Time for n is equal to 10 to the power of 18 times 10 to the power of minus 9 seconds. So this is equal to 10 to the power of minus 9 seconds. Does anyone has a calculator with you? I want to compute how large this one is. Let us do that for a moment now. There are 60 seconds in a minute. There are 60 minutes in an hour. There are 24 hours in a day. There are 365 days in a year. Multiply that for me, please, quickly. Come on, guys. It's roughly 31 million, but check it. Who has a calculator? Come on. I think it's roughly 31 times 10 to the power of second. In other words, there's only 31 million seconds in a day. I'm sorry, seconds in a year. 315. I'll take it. What's that, 3?
3153.
315, that's enough. 10 to the power of? He's counting the zeros now. 7, that's right. That's what I said. 31.5, 10 to the power of 6 seconds in a year. So how many years this is going to be? 10 to the power of 9 divided by 31.5 times 10 to the power of 6 years. Let us do some arithmetic now. I'm writing like Hebrew, but you cannot follow, right? So 10 to the power of 3 divided by 31.5, that is 1000 by 30. 1000 by 30 is roughly what? What is that? How many years? Do you have the luxury of waiting this many years to solve one problem? Okay, let me ask you a question. Are you all with me? Yeah, so a problem of 1 million using the best known algorithm. There's no better algorithm than Cholesky for solving symmetric positive definite matrices. And the best machine money can buy today. Are you with me? Take this much. Now let us ask you a question. Could you wait for a month to solve a problem? Let us see. You suppose you are living in Bangalore in summertime. There is a thunderstorm. There's a lightning. The computer blinks. Your one bit changes and does. We solve so much of power related issues, right? In Bangalore, there's a mandatory power, even assuming you have an uninterrupted power supply. Your uninterrupted power supply is subjected to the vagaries of nature, namely thunderstorms. All of you with me? So even if you say, I have invested money, I'm willing to wait for 6 months, how in the world are you going to be able to guarantee the result at the end of the 6 months is what the paper written in? Are you all with me? Now do you see the difficulty of being large? Why large is, what is the impact of being large? That's what's large. So in computational science, we have two aspects of computation. One is called feasible, another is infeasible. A computation is said to be infeasible if that cannot be done in your lifetime. I'm not saying it's not a computable. I can compute, but my lifetime ain't enough. Are you with me? So the large-scale problems are truly difficult problems because it is not, the large-scale problems are difficult not because I don't know how to solve them. I want you to differentiate that. I know how to solve them, but I may not be around when the solution comes around, depending on the size of the problem. And did you see what he said yesterday? It could be 10 to the power 9 very soon. It's already probably 10 to the 9. You can redo the calculation once again and see how much. So what did we do? We go for parallel computers. But parallel computer can only do so much. So what do? We approximate the solution. We throw the baby out with the bathwater. That's how it happens. Are you with me? So then this now leads to the notion of what's called nonlinear 3D war, and that's what we will do in one of the other talks. Let me stop here. Are there any questions? I already taken 2 minutes into your lunchtime. If there are no questions, we will reconvene at 1. Okay, the boss has an announcement.
I guess I'm not the boss. I'm no. So anyway, so I guess we'll reconvene at 2. But Varun, question for you.
Please. Oh, okay.
Do you mind if I start with the tutorial that I left out yesterday, and then we continue?
Yeah,
later?
I will explain that. You remember yesterday I stole his time, so he's going to steal mine.
Okay, there you go.
So afternoon, the printed schedule says I am going to start, but because of that we want to be nice to each other, so he's going to be steal my time. And then we have a question session, right?
Yeah, but we can continue that.
I'll be here too when he does things. And in the question answer session there'll be lots of questions, and both of us will handle it and help you out.
Right, and I think we could so to say continue the tutorial part into the question session as well.
Absolutely.
So the tutorial will need again laptops, as I said yesterday. So we should start with that. And the plan would be to discuss a few things here. Tell you what the hands-on problems that we would like you to work on. And then you can disperse. You can go to your room, you can go to Mandara, you can go wherever you want, and then we'll reconvene at say 3:30, and then we discuss your solutions. Or if you have problems, we will be around. So if you have a problem, you can come back here, ask us questions, go back and work on it, and so on. So yeah, that's the plan. All of you don't have to sit here and do the hands-on. So you can go to the computer lab and do the hands-on. So if you don't have MATLAB, for example, just go to the computer lab and do that. So yeah, okay.